So we've looked at the arithmetic axioms for the integers, and now we're going to look at the order axioms for the same group. So we're going to review some of the principles of how we choose axioms, and we're going to see how that is reflected in the order axioms for the integers. We're going to list the order axioms for the integers. We're going to prove a theorem about the less than relation, and the less than relation is what tells us how to put the integers in order. We're going to discuss why the arithmetic and order axioms together still don't define the integers uniquely. All right, so again, this is kind of a review from last time, but I want to ask the question, how do we know what axioms are appropriate for a given concept? So first of all, remember that axioms are choices. They are subjective by nature. So, if you don't agree with how we do that here, there's a possibility that there's another completely acceptable way to do it that's different. They should be reasonable, which means that people should be able to agree upon what they are, at least the people who are using the axioms. They should definitely not contradict one another. That can lead to some huge problems. There should be as few as possible, which means that we should not be able to prove one of them from the others. All right, so how do we express the order of the integers? That's a good question. There are infinitely many integers. We can't just simply write them in order. So we use the relation less than to help us out. So when we say A is less than B, that means A comes before B in the ordering. So the less than relation tells us exactly how to order the integers. So here are some properties that we should be able to expect from our order relation. First of all, we should be able to determine the order of any two integers. In other words, if you take two random integers and know what they are, you should be able to say, yeah, this one comes before this one. So if A and B are two different numbers, we should have either A less than B or B less than A. There shouldn't be any ambiguity that they can't be compared. If one number comes before another one, then that first number should come before all the numbers that come after the second one. Otherwise, we'd have an issue of having one number less than another one and then circling around back to the first one. And that's not really an ordering. That'd be a circular type of ordering issue. If we have two different numbers, then increasing or decreasing the numbers by the same amount shouldn't change which one is less than or comes before or after. The order should be the same in both cases. In other words, if I have A coming before B, if I add the same number C to both sides, I should have A plus C less than B plus C. And something similar should happen if we multiply both sides by the same number. Except multiplication is a little bit trickier. This should be okay as long as the number we multiply by is positive. Now, in the previous one where we're adding the same number to both sides, it really doesn't matter where the number that we're adding to both sides is positive, negative, or zero. Adding or subtracting the same number from both sides will still keep the same order. But negative numbers can cause a problem. And to show you why, if we have 4 is less than 6, which is true, if we multiply that by a negative number, and I don't know, say something like negative 2, then we have negative 8 and negative 12, but notice that the inequality flips because negative 8 is less negative than negative 12, so it's going to be greater than negative 12. So the absolute values of the numbers are going to be in the same order when you multiply by a negative number, but when we change the sign, the smaller absolute value becomes bigger than the larger absolute value because they're negative. So here's a more precise wording of the order axioms, and we're going to tell you what their names are as well. The first one is called trichotomy, and what that says that if A and B are integers, then either A is less than B, or B is less than A, or they're equal, right? Those are the only three choices. And that tells us that we can always, given two different integers, we can always tell one of them comes before the other. Transitivity is the one that keeps us from going in a circle, which tells us that if we have three numbers, with A less than B and B less than C, then A has to be less than C. If that were not the case, then we'd have A less than B less than C less than A. That would take us around in a circle. The third one is translation invariance, and that tells us that if we add the same number to both sides of an inequality, it doesn't change the inequality. So if A is less than B, then A plus C is less than B plus C. And then finally, we have the multiplication form of translation invariance, which is called scaling. And that is if you have A less than B, and as long as C is a positive number, so C is greater than 0, then AC is less than BC. Now, it seems like we should probably add that if we multiply by a negative number, then it flips the inequality. In other words, if A is less than B and C is a negative number, then BC is less than AC. And that would be fine to add, except that we can only do that really if we can't prove it from the axioms that already exist. And it turns out we can prove it from the 4 axioms that we have up there. So we do not need another axiom. So the 4 axioms that we have above are perfectly fine for defining order on the integers. So let's go ahead and try proving a theorem. So if I have A less than B and C less than D, then it should be the fact that if I add the 2 smaller ones, it should give us a smaller number than if we add the 2 bigger ones. And that's our theorem. Now, this isn't directly stated in the axioms, but we should be able to prove it from them. Oops. So this looks like a little bit of like translational invariance, so it stands to reason that we might be able to use translational invariance to prove it. So let's see what happens. So if I start with A plus B, we can use translation invariance in 2 ways. We can add C to both sides, or we can add D to both sides, right? So that gives us 2 other inequalities that we didn't have before. And if we look at C is less than D, we can use translational invariance in 2 different ways on that one, by adding A to both sides and adding B to both sides. Now, just to sort of compare things, notice that C plus A is equal to A plus C, and D plus A is equal to A plus D. So if we wanted to flip the order around, that would give us the same number, right? So A plus C is less than A plus D. If we did that to the second inequality on that second line, we get B plus C is less than B plus D. Now, that's a lot to look at, but if we kind of focus on those 2 that I just boldfaced there, the A plus C is less than B plus C, and the B plus C is less than B plus D, that is perfectly set up for translational invariance. Or not translational invariance, I'm sorry. The transitive property. Because if we put those together, we get A plus C is less than B plus C, which is also less than B plus D. So we can use the transitive property to get A plus C is less than B plus D. And actually, we can. That's not the only way we can do that. We can get the same result by looking at those 2 I just boldfaced. So there we have A plus C is less than A plus D on the bottom there. And then A plus D is less than B plus D up on the top. And again, using the transitive property, we can get the inequality that we want. So by using translation invariance and the transitive property, it looks like we can get the theorem that we want. All right, so here's what the proof is going to look like, or I should say a proof is going to look like. There are at least 2 out there that we could use. So we're going to assume that A is less than B and C is less than D, and we're going to show that A plus C is less than B plus D. So by translation invariance, since we have A is less than B, we're going to add C to both sides to get A plus C less than B plus C. Since C is less than D, we're going to add B to both sides to get C plus B is less than D plus B. We're going to use the commutative property to rewrite that as B plus C is less than B plus D. Then, since we have A plus C less than B plus C and B plus C less than B plus D, we can use the transitive property to get A plus C is less than B plus D, and that proves our theorem. And as we noted on the previous slide, if we add D to both sides of A less than B, and if we add A to both sides of C less than D, we can use the transitive property on those inequalities to get the same thing. All right, so once again, I want to ask the foundational question, do the arithmetic and order axioms define the integers together? So we added some axioms. Does that maybe make the integers, a little bit more precise? And well, the answer again is no. And for basically the same reasons as before, right? Adding those order axioms didn't narrow anything down. The rational numbers and real numbers satisfy those order axioms as well, so they didn't really do us any good. We still have the same issues about the axioms being descriptive, describing what the integers are like, rather than constructive, telling us why the integers exist, how we can actually construct the integers. And as I mentioned before, we really need Peano's axioms and some additional definitions to get that constructive part to work. However, just like before, we're going to accept these axioms as true to prove theorems about the integers, and hopefully can find another axiom that narrows things down beyond the rational numbers and the real numbers. But in the meantime, all you have are some order axioms activities to work on. They're on the PDF file included with this video.